Okay, guys, all you need at your desk is something to write with. You need nothing else, so everything else should be gone. It might get in the way, because you are going to be moving a little bit, eventually. So, okay. Now, guys, first of all, let me give you something. This is just a summary sheet. What we're looking at today, guys, is how to find all the properties of a rational function and then how to graph it. Okay? Now, when you learned this last year in Math 3, you took actually about a week and a half to do it. We're gonna do it in 15 minutes.
Oh, yeah. The way you think we're not smart.
Oh, I know you're that smart.
I mean, I'm sure David is, but I don't
Okay,
know.
here's just kind of a summary sheet. You can write all over this. Oh, don't worry about it. I'll get you around here. You can write all over this if you want. Okay, and I would definitely kind of make your own notes. But let me run through everything with you. Anybody not have one of these? Whoa. Cameron? Or join table 1. Sam's still waiting for his significant other.
Still waiting for
I don't know what else to call the person. Partner?
Partner. It was perfect.
What? Significant other? Or insignificant other? That's what my wife calls me. It's correct, actually.
Can I see papers?
No, you can't.
Can I borrow paper?
No. You can buy one, it'll cost you $1.
That's fair.
I'll put it on your bill.
I don't play poker for it.
You do realize that I'm charging you money, I'm gonna bill all of you at the end of the term, right?
Sick.
It is a little sick. I'm not sure if it's legal, but I'm gonna do it anyway. Okay. Whew, ready? Okay, we're not gonna end with just me, but we're gonna start, I'm gonna cram this down your throat as fast as I can do it. Okay? So, pay attention. You can go ahead and take any extra notes or whatever you're wanting to do, kids, the kind of things. Now, the steps that I'm going to give you aren't going to quite line up with steps here, and I apologize. I put them in a different order when I wrote down this and wrote down all this kind of stuff. But first thing I want to look at is rational functions. By the way, if you can't see from where you are, you're welcome to move up and move with me. That's fine. I don't care. Okay, rational functions are where we have a polynomial over a polynomial. Okay, easy stuff. So you can see examples if you look at the posters around the room of all kinds of things. X squared plus 3x minus 4 over 2x squared minus 4, that kind of thing. The very first thing you always want to do with polynomial expressions before you start anything is factor. Factor, 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 factor. Factor everything. Okay? And the big, huge idea, rational functions are all about their asymptotes. And there's only one S in asymptotes. I spelled it with 2 S's for a long time. Once you got, I did, until somebody says, Mr. Dick, do you know there's only one S in there? I was like, oh, maybe I just had a bad opinion of asymptotes. I spelled it with 2 S's. Okay. Once you've factored everything, you've got to find the domain. Now, this domain is not anything new. We've done these kind of things before. The problem is the denominators can't be equal to 0 because that's where they're undefined. So what you do is you find where they do equal 0. So you find the zeros of the denominator. The domain is always going to be, the easiest way I think to put it is in set builder notation, x such that x can't equal all the zeros of the denominator. You could do it, negative infinity to the lowest 0, next 0 to that 0. You could go that way, build a whole bunch of intervals, tie them together. We've done that before. Okay, now once you've found the asymptotes, or once you found your domain, now sometimes your fraction can be reduced. For example, this one, you have x plus 1 over x minus 2 over x plus 1. The x plus 1's cancel. Whenever you have a factor that cancels, a hole is made there. A literal hole in your function where the function's going along, and then has a hole. And then it continues on. Okay? On a graph, I make that by putting a little empty dot, little empty circle over there. Okay? So any canceled factors, the zeros will give you that hole. Now there's a pro tip. It is a little difficult to see here. Wonder if I can get any higher. I can't. There's nothing higher here. Anyway, pro tip kind of things. The x-coordinate of the hole is found from the 0 of that thing that was canceled. The y-coordinate of the hole you can actually find by putting the x value into your reduced equation and solving it from there, okay? Now, holes. So you found that you factored it, you found the domain, you found any holes that are there. Now let's get on to the asymptotes. First things we're going to look at is vertical asymptotes. I've got 3 kinds of asymptotes, Lauren. I can have a vertical asymptote, I can have a horizontal asymptote, and sometimes we even do it slantwise. That sounds dirty, but whatever. Vertical asymptotes, horizontal asymptotes, slant asymptotes. Vertical asymptotes are always located at the zeros of the denominator. So I look at the denominator. This particular denominator has 3 factors: x, x plus 2, x minus 3. Therefore, it has 3 asymptotes. At x equals 0, x equals negative 2, and x equals 3. Those are the 3 zeros of that denominator. You always represent asymptotes as equations. They are never lines. Where's the asymptote? At 4? Bullpucky. That's wrong. It will not be 4. Asymptotes are lines, therefore they have equations. X equals a number is the vertical. Okay? We represent them with dashed lines. Cool. Okay, moving on. Non-vertical asymptotes. And I lump non-vertical asymptotes with horizontals and slants, or obliques. Those are the same things. Don't care which word you use. To find the non-vertical asymptotes, first of all, you look at the degree at the top and the bottom. The degree is the highest exponent, remember? Or if it's already factored, it's the number of x factors. So like there, degree of 2, degree of 3, degree of 2. Or if I was to look over here, here's 2 x's and there's 1, so degree of 2, degree of 1. Okay? If the top, there's only 3 cases. Either the top could be higher, the bottom could be higher, or they could be the same degree. If the top is higher, well, let's start with the easy one. If the bottom is higher, there is a horizontal asymptote, and it is at y equals 0, always. If the bottom degree is higher, it has a horizontal asymptote at y equals 0. If they have the same degree, so like this, x squared over x squared, there is a horizontal asymptote. It's located at the coefficient, the leading coefficient of the top, divided by the leading coefficient of the bottom. Okay? Leading coefficient of the top over leading coefficient of the bottom. You just have to reduce it, like 2 over 1. If the top is higher, that's where you have to do a little bit more work. If the top is higher, well, let me back up. If the top is higher, it might have an oblique. If the top is exactly 1 degree higher, then it does have an oblique. So if it's like an x to the 4th over x squared, it doesn't have any non-vertical asymptote. But if the top is exactly 1 degree higher, then you can divide the top by the bottom. So in this case, I would take x cubed minus 3x squared plus 2x plus 1. I'd take all that divided by the x squared minus 1, and I end up getting x minus 3. Now, I did long division here because where I'm dividing by x squared minus 1, I can't do synthetic division. I have to do long division. If you could use synthetic division, if this was a linear divisor in the denominator, you could do synthetic division. Awesome. I take that, divide it, and I get this. Now, notice on the division, I did x cubed minus x cubed divided by x squared is x. So I multiplied x times here, x times x squared is x cubed, x times negative 1 is negative x. I changed my signs, dropped all the things, dropped the negative 3x squared. Negative 3x squared divided by x squared is negative 3, and I stopped. I didn't finish the division problem. You don't have to, because your slant asymptote is always the non-remainder. So as soon as you fill this space up here, you're done. I don't need to actually finish the whole thing. So my slant asymptote is y equals x minus 3, which has a y-intercept at negative 3 and a slope of 1, so I put a dashed line there. Now, I have asymptotes. Okay, whew. Next I want to find some intercepts. I've got 2 different kinds of intercepts. I've got x-intercepts and y-intercepts. That goes, oh, Luke has one, okay. Oh, Lauren doesn't have one, I'm sorry, Lauren. X-intercepts and Y-intercepts, we found these before. The Y-intercepts, put 0 in for X and then simplify it. So like here, if I have this, I let X equal 0 and I get 0 minus 1, 0 minus 2, 0 plus 3, simplify that to 2/3, and I've got 0 2/3. Okay. X-intercepts, you set the numerator equal to 0. I set the numerator equal to 0 because if the numerator equals 0, 0 divided by whatever the denominator is 0. And anytime the whole function equals 0, that means I've got an x-intercept. It's crossing on the x-axis. So if I set the numerator equal to 0, x times x minus 1 equals 0, I get two zeros. 0 and 1. So my intercepts are at 0, 0 for this one, and 1, 0. By the way, anytime you see 0, 0, you have found both a y-intercept and an x-intercept. There can be, won't always be, one y-intercept. There can be lots of x-intercepts. Now, moving on. Moving on. Something else we need to think about is your non-vertical asymptotes. Oh, by the way, whatever teachers you had that said asymptotes are never, it's never going to cross your asymptote lied. They lied. A vertical asymptote on a rational function will never be crossed. If you ever cross a vertical asymptote, you're going to hell. Period. It's that bad. A non-vertical asymptote can be crossed. Because a non-vertical asymptote, see, asymptotes are all about the end behaviors. It's getting closer and closer to the asymptotes. Non-vertical asymptotes, they can actually cross in the middle. So you've got to figure out, does it cross? The way you figure out, does your function cross your non-vertical asymptote, is you set your non-vertical asymptote. You see that what I did? NVA, non-vertical asymptote. You set it equal to your expression and then you solve it. So for example, on this expression, x squared plus 1 over x squared plus x minus 12 had a horizontal asymptote at y equals 1. So I set this thing equal to 1 and I solved it. Now, something you're always going to do when you're solving these is you're going to multiply by the denominator, right? Always. So that would cancel, and I'd end up getting this. My x squareds would cancel. I'd get 1 equals x minus 12, and I get x equals 13. If you're able to solve that equation and get a value for x, that's a yes, it crosses. In fact, it's going to cross at x is 13, and the y value is 1. It's going to cross at that exact point. This one, for example, x plus 1 over x minus 7, I'd multiply by x minus 7 on each side after I set this equal to 1. And I get x plus 1 equals x minus 7. The x's cancel and I get 1 equals negative 7. Well, that's not true. This wasn't able to be solved. So no, that one's not going to cross at all. Okay, now, the last thing we need to look at is, let's put it all together.